Okay, now exercise 32. So here we have been asked what is the largest bet that cannot be made with chips worth $7 and $9 in places where gambling takes place, such as a casino. It's usually too dangerous to place bets directly with actual money. So what a player does, or what a gambler does, he or she goes to the casino and pays some amount of money and to the casino, and they in turn give an equivalent amount of chips, and those chips can then be used to place bets. So if we use chips of this much values, then what is the largest bet that cannot be placed, that cannot be made? For example, if you are using, say, m number of chips of this type and n number of chips of this type, then the total value of your bet will be 7m plus 9n dollars. Okay, so essentially this exercise asks us to find out the number, the largest integer that is not of that form, 7m plus 9n, and we have to verify our answer with both forms of induction, that is ordinary induction as well as strong induction. So let us see how the solution goes. Since we will be dealing with numbers of the form 7a plus 9b, so we start by considering a set of such numbers. Let S be the set of numbers of this form 7a plus 9b, where a and b are integers and they are non-negative, because a and b both represent numbers of chips, so it does not make sense to consider them negative. Also, someone may decide to not use chips of this type at all in placing some bet. So we have to have the provision for taking b to be 0. So that's why we have chosen a and b to be non-negative and not just positive. Okay, now this is the claim we are making. We claim that the largest integer not belonging to S is 47. To prove this claim, we have to show two things. The first is that 47 does not belong to S, and the second one is that every integer greater than or equal to 48 belongs to S. So we first show that 47 does not belong to S. To the contrary, we start by supposing that it does belong to S and then arrive at a contradiction. Suppose 47 belongs to S, then 47 is of that form 7a plus 9b for some non-negative integers a and b. Okay, non-negative integers a and b. Now, is it possible for any one of them to be 0? Clearly from this equation both a and b cannot be 0, because in that case the right hand side would be 0. Can one of them be 0? Say if a is 0, then the equation becomes 47 equal to 9b, but since b is an integer, that would imply that 9 divides 47, which is not true. so A cannot be 0. Similarly, since 7 does not divide 47 also, so B cannot be 0. So we write like this: since 7 does not divide 47 and also 9 does not divide 47, both A and B are positive. So A and B both have to be positive. Since 9 times 6, which is 54, is greater than 47, we must thus have this. If we take B to be 6, then 9 times 6 becomes greater than 47. Since A is non-negative, so then the equation cannot be satisfied for such a choice of B. Or if you take B higher, then the situation becomes even worse. So that's why B cannot be greater than or equal to 6. That means B has to be less than or equal to 5. At the same time, since B is positive, so B is greater than or equal to 1. Okay, so now we have finitely many choices for B: 1, 2, 3, 4 and 5. But none of the integers, you can see this, 47 minus 9, that is 38. 47 minus 9 times 2, that is 29. Then 47 minus 9 times 3, that is 20. Then 47 minus 9 times 4, which is 11, and 47 minus 9 times 5, 2 is divisible by 7. If this equation is truly being satisfied by some integers A and B, then for the possible choices of B, for at least one of them, 47 minus 9B should have been divisible by 7. But in all the possible cases, that is not the case. None of these integers, 38 or 29, 20, 11 or 2, is divisible by 7. So this is the contradiction. This is a contradiction and proves that our supposition is wrong. That is, 47 does not belong to S. Okay, let me put some ink. I would run out of it quickly. Now next we have to prove that every integer greater than or equal to 48 belongs to S. And in this part you can understand we have to apply induction. It is here that we will apply both forms of induction. Next, we prove that n belongs to S for all integers n greater than or equal to 48. So our induction now starts with 48. So we first of all have to show that 48 belongs to S. So it should be expressible as 7a plus 9b for some integers a and b. You can see that this is 7 times 3 plus 9 times 3. 9 plus 7 is 16, 16 times 3 is 48, which implies 48 belongs to S. Now induction hypothesis. Assume that n belongs to S for some integer n greater than or equal to 48. Now since n belongs to S, so n should be of this form. Then n is equal to 7a plus 9b for some non-negative integers a and b. Okay, now our aim is to show that n plus 1 also belongs to S, and for that we can do these things. If b is greater than or equal to 3, then n plus 1 is equal to 7a plus 9b plus 1 can be written like this: 7 times 4 minus 9 times 3. 7 times 4 is 28 and 9 times 3 is 27. So this is 1, and this is equal to, now if you rearrange the terms, then this becomes 7 times a plus 4 plus 9 times b minus 3. Because b is greater than or equal to 3, this b minus 3 is a non-negative integer. So now this number again is of the required form for it to be an element of S. So this belongs to S. Now assume, so this is the case when b is greater than or equal to 3. B to be less than 3. If we suppose a to be less than, say, 5, then 47, no sorry, not 47, what am I writing, not 47, then n, which is 7a plus 3b, would be less than or equal to, what is the largest value of b? I mean, b is less than or equal to 2. So if we replace b by 2, we get this. Similarly, the largest possible value according to this inequality of a is 4. So this is 7 times 4. So this is 28 plus 6. So this is 34. But this clearly is not possible, because according to our assumption n is greater than or equal to 48, then this, which is not possible, so that means our supposition is wrong. So we must have a greater than or equal to 5. In this case, n plus 1 is 7a plus 9b, and now 1 can be written like this: 9 times 4 minus 7 times 5, 36 minus 35, that is also equal to 1, and this is equal to 7 times a minus 5 plus 9 times b plus 4. Now since a is at least 5, so a minus 5 is a non-negative integer, so this again has the form for it to be in S. So by the first principle of induction, which is theorem, (0.5) n belongs to S for all integers n greater than or equal to 48. So we have proved what we wanted to prove using the first principle of induction. Now next we apply the second principle of induction to prove this second part. Same thing, but using the second principle. We have already seen that 48 belongs to S. Something else also belongs to S. Many other higher numbers belong to S, and then that can be shown directly. Note that (49), which is 7 times 7 plus 9 times 0, this belongs to S because it has the required form 50. 50 can be written like this: 7 times 2 plus 9 times 4. Then 51 is 7 times 6 plus 9 times 1. Then 52 is 7 times 1 plus 9 times 5. Then 53 is 7 times 5 plus 9 times 2, 54 is 7 times 0 plus 9 times 6, and 55 is 7 times 4 plus 9 times 3. All these numbers belong to S. Okay. Let n greater than 55 be some integer such that m belongs to S for every integer m less than or equal to n and greater than or equal to 48. Oh, strictly less than n. So this is our induction hypothesis for the strong induction. We are assuming that there is a, suppose there is an integer n greater than 55 such that the integers starting from 48 up to the integer n minus 1 are all in S. If we can now show that n also belongs to S, then by the strong induction principle we will be able to conclude this statement again. Okay. Since n minus 7 belongs to S. Okay, now n minus 7 is what? N minus 7 clearly lies in this range, because you see, if you take n minus 7, here what will you get? If you subtract 7 from this, you will get 41 less than or equal to m minus 7 less than n minus 7. Okay. Now n minus 7 is clearly less than n because 7 is positive. So n minus 7 will be strictly less than n, but n minus 7 at the same time is greater than or equal to 41. So because of our induction hypothesis, n minus 7 will belong to S. So since n minus 7 belongs to S, we have n minus 7 also of that form is equal to 7a plus 9b for some non-negative integers a and b. Thus, so what then happens to n? If we add 7 on both sides, we get this 7 times a plus 1 plus 9b. Again, this is of the required form, so it belongs to S. So we have proved that n belongs to S. Hence, by the principle of strong induction, or by the second principle of induction, which is theorem 0.6, n belongs to S for all integers n greater than or equal to 48. So using both forms of induction, we have proved that the statement is true, and that's why we have finally proved that $47 is the largest bet that cannot be made using such chips. Okay, now before I move on to the next exercise, let me just quickly verify one thing. Is this conclusion correct? N minus 7 belongs to S. N minus 7 is strictly less than n, there is no doubt about that. Okay, there is no doubt about that, but at the same time n minus 7 is greater than something. Okay, because n is greater than 50. Okay, that's why we have been writing all these things. No, so I forgot to tell you one thing. N minus 7 is less than n, that is fine, but because n is greater than 55, this is 55 minus 7, which is 48. So n minus 7 lies in the range that it is less than n but greater than 48. So that's why we are able to use the induction hypothesis to conclude that n minus 7 belongs to S. Yeah, now it makes sense. Okay, so the next one, exercise 33. And this is a theoretical one. Prove that the first principle of mathematical induction is a consequence of the well ordering principle. Mathematical induction is a consequence of the well ordering principle. Okay, so that means we will assume that the well ordering principle is true, and from that we have to prove the first principle of mathematical induction. Let S be a, or instead of writing it in words, let's use symbols. Let S be a subset of the set of integers and A be an integer in S. Okay. Suppose now we have to assume the condition for the first principle of induction, that S has the property that whenever there is an element in S, then the successive element is also in S. Suppose n belonging to S and n greater than or equal to A, these two things imply n plus 1 also belongs to S. The first principle of induction under these conditions tells us that then S contains all integers greater than or equal to A. That is the first principle. Now we have to prove that. Okay. And we will do it like this. Define a set, a new set T, that is this n minus A plus 1 such that n belongs to S and n is greater than or equal to A. Note that this n is general. N is any element in S. At the same time, n is greater than or equal to A. But whatever n may be, since this inequality is true, so that means n minus A is greater than or equal to 0, and so n minus A plus 1 is greater than or equal to 1. So all the elements in T are positive integers. That means T is a subset of the set of positive integers. Since n is greater than or equal to A, we have this. T is a subset of the set of positive integers. Subset symbol is actually this in this book. So previously if I used the other symbol somewhere, please change it accordingly. Okay, this means subset. So we have this. Also T is non-empty because 1 which is A minus A plus 1, this belongs to T. Okay, now why does 1 belong to T? 1 has this form, namely when you take n equal to A, you can take n equal to A, that is allowed in this inequality. And one more thing is that A is in S. See the choice? So that's why in place of n we can take A, and when we do that we get 1. That's why 1 is an element in T, and as such T is non-empty. Now what are the things we have got? T is a non-empty subset of the set of positive integers. So by the well ordering principle, T will have a least positive integer, I mean a least element. So by the well ordering principle, T has a least element B. Say we call that least element B. We claim T is equal to the set of positive integers. This is our claim. We are now going to prove this claim. Suppose I think I made a mistake, sorry. It's not the least element of t that we have to take. Okay, sorry about this. But it's the least element of something else. Yeah, that's why I was thinking it looks kind of off. Something is amiss. Okay, so this part there is no problem. T is a subset of Z plus and T is non-empty. But then do we really need to say something about non-emptiness of T? What does the hint say here? Okay, it does not hurt to notice that T is non-empty. It may or may not be useful later on, but we will figure that out. Let's just go with the solution. Now we claim that T is equal to Z plus actually. Suppose T is not equal to Z plus, then Z plus minus T is a non-empty subset of Z plus. This difference by definition is a subset of Z plus, and because T has now been supposed to not be equal to Z plus, so this is non-empty also. Now on this set we are going to apply the well ordering principle. So by the well ordering principle, Z plus minus T has a smallest element B, say. Okay. The fact that 1 belongs to T will play a role, although not in concluding that T is non-empty, in concluding something else. In concluding this, since 1 belongs to T, we must have this. Note that B is the smallest element of Z plus minus T. That means B is a positive integer. But 1 already belongs to T, we have seen that here. So B cannot be equal to 1 because B is not in T. Since this is the smallest positive integer, so B has to be strictly greater than 1. Then B minus 1 is a positive integer. Because B is greater than 1, B minus 1 is a positive integer. That is less than B. Being a positive integer, B minus 1 is in Z plus. Okay. Now the question is, does it belong to T or not? B is the smallest element of z plus minus t. Since this is smaller than B and still it's in z plus, so it cannot be in z plus minus t, but then because it belongs to z plus, it is then forced to be in t. So this implies b minus 1 belongs to t. Hence b minus 1, since it's in t, it will be of this form: n minus a plus 1 for some n belonging to S satisfying this. Okay. This thing implies B is equal to n plus 1 minus a plus 1 okay. B then is equal to this. Note that from the condition on S, this condition, don't forget that S satisfies this condition, that whenever we have an element n in S and n is greater than or equal to a, then n plus 1 also belongs to S. Now here n is an element in S and n is greater than or equal to a. So we have n plus 1 belonging to S. So what is the current situation now? B has been written in this form n plus 1 minus a plus 1, where n plus 1 is in S and n plus 1 is also greater than or equal to a. In fact, it is strictly greater than a. We thus have B is equal to n plus 1 minus a plus 1, where n plus 1 belongs to S and n plus 1 is greater than or equal to a. Now you look at the definition of T. The definition says that B has to be in T because B satisfies all the conditions that are required for something to be in T. Hence, B belongs to T, which is a contradiction because we have chosen that B is the smallest element in Z plus minus T. As such, B is not in T according to this, which is a contradiction. So our supposition not equal to z plus is wrong. That is, we must have t equal to z plus. So we have proved our claim, but this is not what we are after. We are after something else. We wanted to show that the set S contains every integer greater than or equal to a. Now using this equality, we are able to show that. Now let n be a, or let n greater than or equal to a be any integer n greater than or equal to a be any integer. We want to show that n belongs to S. Then n minus a plus 1 is a positive integer from this inequality. We get the fact that n minus a is non-negative. Add 1 to that, you get a positive integer. That is, n minus a plus 1 is an element in z plus, but because of this equality, it is an element in t also. Hence, n minus a plus 1 will have the form that the elements in t have, that is, it will be of the form m minus a plus 1 for some m belonging to S satisfying m greater than or equal to a. Now what do you get from this equation? Minus a and plus 1, they cancel out, so we are left with n is equal to m. Thus n is equal to m, but m belongs to S, so n also belongs to S. Thus, we have already written thus. This implies S contains all integers n greater than or equal to a, which is nothing but the first principle of mathematical induction. This is the first principle of mathematical induction. So the the truth of the well ordering principle implies the truth of the first principle of mathematical induction, and the converse is also true. One can prove that if the first principle is taken to be true, then the well ordering principle is also true. It also comes as a consequence of the first principle of mathematical induction. In other words, they are equivalent, logically equivalent. Truth of any one of them implies the truth of the other. Although both of them are equally plausible, I mean, if we just think about it, thinking that the first principle of mathematical induction it's quite natural. It makes us believe that it is true. Just like that, the well ordering principle also makes us believe that it is true. Just from the sheer statement that if you consider the set of all positive integers and there you consider a non-empty subset, then you feel that there must be some left boundary, that is, there should be a smallest element, and that's the well ordering principle. Okay, now we next look. I need some ink before that. Next, 34. The Fibonacci numbers are defined by are. First, they are writing just the numbers. In general, the Fibonacci numbers are defined by these formulas. F1, F2, Fn denotes the nth Fibonacci number. F1 and F2 are defined to be equal to 1. You can see from the sequence that each except the first two, every other term is a sum of the previous two terms. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. That's how the sequence of Fibonacci numbers is generated. And for n greater than or equal to 3, Fn is defined to be equal to Fn minus 1 plus Fn minus 2. Prove that the nth Fibonacci number Fn satisfies this inequality, that it's always less than 2 to the power n. We can use induction to prove this. Note that F1 by definition is 1, which is less than 2, that is 2 to the power 1. So the inequality is true in the case n is equal to 1. Like that, F2 is also 1, which is less than 4, that is equal to 2 square. Now assume that Fm if m is less than 2 to the power m for all integers m lying between 1 and n, let us take like this, where n greater than or equal to 2 be some integer. Let's take less than or equal to n. We will have to now prove the inequality that if n plus 1 is less than 2 to the power n plus 1. So here note that the induction hypothesis, the assumption that we made, it looks like the assumption that we use in strong induction principle or second induction principle. So that's what we are doing here, because to carry out the induction step, since we need two previous terms, so that's why we need to use the second principle of induction. And the reason for considering n to be greater than or equal to 2 is that when you take n plus 1, you will then be considering fn and fn minus 1. Fn plus 1 is the sum of fn and fn minus 1. So if n has the least possible value 2, you will then have f2 and f1. Beyond which, preceding which there is nothing. Things start with f1. So that's why we have taken n to be at least 2 for some, okay, let this be some integer. Then fn plus 1 by definition is, now note that since n is at least 2, so n plus 1 is at least 3, so we are able to use the formula n minus 1. Now from our induction hypothesis, we conclude that this is less than 2 to the power n and this is less than 2 to the power n minus 1. Now note that 2 to the power n is actually 2 times 2 to the power n minus 1. So this is 3 times 2 to the power n minus 1, which is less than 4 times 2 to the power n minus 1. The fact that 4 is equal to 2 square then gives us this. So fn plus 1 is also less than 2 to the power n plus 1. So by the second principle, of mathematical induction, if n is less than 2 to the power n for all integers n greater than or equal to 2, because that's how we have chosen. Since we also have f1 less than 2 to the power 1, we conclude that fn is less than 2 to the power n for all integers n greater than or equal to 1. So this completes the solution. Next exercise 35. Prove by induction on n that for all positive integers n cube plus n plus 1 whole cube plus n plus 2 whole cube is a multiple of n. Oh, sorry, not multiple of n, multiple of 9. Okay, this we have to prove, and using induction we have to prove this, not using some number theoretic techniques. So the first case is of course n equal to 1 because it has been said positive integer. So 1 cube plus 1 plus 1 whole cube plus 1 plus 2 whole cube turns out to be equal to 36, which is a multiple of n. We know this. Multiple of 9, sorry, I am saying n again and again. So this is the basis for our induction. Assume that this is a multiple of 9. For some positive integer n. Now, what happens if we take n plus 1 in place of n in this expression? We then get this. Now we keep these two things as they are. And we expand this. So this will be n cube plus 3 times n square 3. That means 9 n square plus 3 times n times 3 square. That means this is 3 cube 27n plus 3 to the power 3. No, sorry, not 3 to the power 3. Is it 3 to the power? Wait, I think I am confusing myself. N cube plus 3 times n times, sorry, 3 times n square times 3. So this is 9n square, fine. Plus 3 times n times 3 square. So that 3 and 3 square give me 3 cube, which is 27. Along with that we have n plus finally 3 cube. Okay, so that is again 27. Since now in this sum you look at this, by the induction hypothesis this is a multiple of 9 and the rest is also a multiple of 9, since 9n square plus 27n plus 27 is a multiple of 9 and also this is a multiple of 9 by the induction hypothesis. So this is also a multiple of 9. This completes the induction and completes the solution also. Okay, then exercise 36. Suppose that there is a statement involving a positive integer. Involving a positive integer parameter. Parameter n, and you have an argument that shows that whenever the statement is true, for some particular n, it is also true for n plus 2, not n plus 1 but n plus 2. Suppose you are able to prove this. what remains to be done to prove that the statement is true for every positive integer. This is one half of the question, and then the second half is describe a situation in which this strategy would be applicable. Okay, so we have some statement pertaining to positive integers such that truth of the statement for some particular positive integer n implies its truth also for n plus 2. Now, what should be done extra? I mean, apart from this, what else should be done so that the statement turns out to be true for every positive integer? And we also have to describe a situation in which this strategy would be applicable. The first part I have solved. For the second part, I could not I was unable to come up with a situation in which this strategy would be applicable, in the sense that this strategy is the convenient strategy to apply, not the usual induction. Okay, so I leave it to you to figure out such a situation in which, if you show that if a statement is true for n, then it is also true for n plus 2, and this is much easier to show than showing that truth of Pn implies truth of Pn plus 1. This is easier to show. You have to come up with such a statement. Then with the help of this exercise, or what we will write as the solution to the first part, it will imply that the statement is true for all positive integers. Okay, so I write it like this. It is enough to prove that the statement is true for n equal to 1 and n equal to 2. Why is that so? You see, when you choose n equal to 1 and you show that the statement is true for n equal to 1, then your argument that shows this will then tell you that the statement is also true for n equal to 3, and then from that it will also be true for n equal to 5. So for all odd positive integers, the statement will be true. Your proof that it's true for n equal to 2 will imply that similarly that the statement is also true for all even positive integers. So that's why the statement would be true for all positive integers, since every positive integer is either even or odd. So we will have covered all the cases. But here I cannot end the solution, because ideally I should have come up with such a statement, which I so far haven't been able to find. So this I leave to you. I will also think about it, and if I come up with it, I will let you know. So this part is incomplete. Then exercise 37. In the cart named as from songs in the key of life, Stevie Wonder. Mentions the equation okay, so it's a reference from some song or something. I'm not really aware of what it is referring to, but we are really interested in this equation. That's all we need to know. Find all integers in for which the statement is true. That means for which the equation is true. Or we have written the equation. Same thing is true, but modulo n. If you just treat them as ordinary integers, clearly this is not true. 8 cube is not equal to 4, but modulo n they may be equal. Where, however, you have to think of them not as ordinary integers, but you can think of them as integers, but then you have to keep that modular relationship between them. If two integers are they leave the same remainder when divided by n, then they are considered to be equal. Okay, in that sense. For an integer n satisfying eight cube minus 4 mod n equal to 0, n should be clearly n has to divide, then n has to divide 8 cube minus 4. So n should be a divisor of 8 cube minus 4. So the required integers are the divisors of 8 cube minus 4. should be a divisor of 8 cube minus 4, which is 508. So you choose any divisor of 508, then modulo that divisor 8 cube will be equal to 4. For example, you can take n equal to 2 or some other divisor of 508, that would do. Exercise 38. Prove that for every integer n, n cube mod 6 is equal to n mod 6. Note that for any positive integer n, if we are able to prove that n cube mod 6 is equal to n mod 6, then this implies minus n whole cube mod 6 is also equal to minus n mod 6, because you can then multiply both sides of this equation by minus 1, giving you this equation. So if you prove this equation for positive n's, you automatically have the equation for negative n's. Also 0 cube mod 6 is equal to 0 mod 6, because both are equal to 0. So it's enough to prove this for all positive integers n, and in doing so we will apply induction on n. We have 1 cube mod 6 is equal to 1 mod 6, because both are equal to 1. We are not writing that, okay, you already know both of them will be equal to 1. Now we make the induction assumption, that is hypothesis. Assume is equal to n mod 6 for some positive integer n. Then n plus 1 whole cube minus n cube. If we expand the first term, we get n cube plus 3n square plus 3n plus 1 minus, oh sorry, why have I written minus? No, it's not minus n cube, sorry. I needed to consider this. So then this becomes n cube plus 3n square plus 3n plus 1 minus n minus 1. So this becomes n cube, 1 and minus 1 they cancel out, n cube minus n. So should I keep, yes, n cube minus n, and the remaining ones are this 3n square plus 3n. The induction hypothesis tells us that 6 divides n cube minus n. By the induction hypothesis, six divides n cube minus n. Note that two divides n square plus n, because n square plus n is n times n plus 1. If n is even, as a positive integer, n will be either even or odd. If n is even, then definitely 2 divides n. If n is odd, then n plus 1 is even. So that is divisible by 2. So in any case, this product is always even. It is divisible by 2. And hence 6 divides 3 times this, that is 3n square plus 3n. So 6 divides both this as well as this, hence 6 divides that one. Thus we have this 6 divides n plus 1 whole cube minus n plus 1, or n plus 1 whole cube mod 6 is equal to n plus 1 mod 6. Thus by induction we write in short, what we really mean is that by the first principle of induction, n cube mod 6 is equal to n mod 6 for all positive integers n. That completes the solution. Okay, next exercise 39. Okay, this is a very interesting one, again using modular calculations. It's about time. If it is (2 a.m. now), what time will it be (3,736 hours later? Hours from now. Okay, if it is 2 a.m. In the morning, ideally we should say, although it's night. Now then, after 3736 hours, you have to say the time. You have to tell what time it is. Since 3736 is equal to, if you divide this by 12, you get this 311 times 12 plus 4. The time is 6 p.m. But why? You see, suppose you have 2 a.m. right now. After 12 hours, it will again be 2, but that will be 2 p.m. One more 12 hours will again give you 2 a.m. So if you go like this, if you perform one revolution, one complete revolution, then you come back to 2 of the clock. But AM and PM is decided by how many times you had to make the revolution. If you make it only once, AM becomes PM. If you make it twice, then again we come back to AM. If you make it 3 times, then again it becomes PM. So that means this number here we have to make 311 complete revolutions. Since this number 311 is odd, so AM will turn into PM. After making 311 revolutions, you will come back to 2. But it will be 2 p.m. because this is odd, 4 hours extra. So that's why 2 plus 4, 6 p.m.